All right. So I wanted to do a quick recap of what I've been up to the last couple of days since the last stream. So what you just saw was live streamed directly from my Nintendo 64, the video stream. So currently I have a setup where I've connected the raw RGB data, or the raw data pins that go into the video DAC to an FPGA, a Glasgow. And I wrote an applet that handles or reads that data and converts it into pixels. And then I send that to my computer, and in there I turn it into an FFmpeg stream. So, and then using Video for Linux, I convert that to a webcam sort of thing, which I can then load into OBS. So that's what you just saw. So it's live, and the latency is pretty good. It's kind of fun. So the way it works is that I have this Glasgow applet. Let's bring that up. So I guess we can start here. Yeah, maybe this is annoying to look at. So yeah, where should I start? Maybe with the protocol, I guess. So let me just bring up the correct information. I have too many bookmarks and tabs. Let's see here. So we go to the video interface, and it looks like this. So I've connected these pins to my FPGA, to the Glasgow, which is a 7-bit data bus with a synchronous or a sync signal and a clock. And depending on the sync signal, it tells us which kind of data we are getting on the bus. So if it's when the sync is low, we get one cycle of these signals. So it's a composite signal, horizontal sync, and clamp, and VSync. And then on the following 3 cycles, we get R, G, and B values. So using this information, we can then sample the R, G, and B values and then send those into to the host computer, which then can turn that into a picture. So I struggle a bit with the sync signals because these are kind of raw VGA. What does clamp do? Yeah, exactly. So honestly, I haven't really figured it out. I did something quite nasty. So the last 2 days, I kind of tried to wrap my head around how this stuff actually works, but I don't know, I just got stuck. So what I'm doing is basically something quite ugly, where I do, let's see here. So let's just go through the code quite quickly. So here I'm using a flip-flop chain to sample the signals. And this is clocked using the external clock. So using this clock signal, we are sampling the external signals, and then they are being fed into a chain of flip-flops. So we are sort of certain that we can read those signals, and we don't get any weird sampling issues. And then here's my ugly code. So let's see here. I have this counter which basically just counts up in order to figure out where in the sync phase we are. And then I unpack the sync signals from the data. So DI is the safe to read data bus. And I store those. And then I also check that I also store the old sync so that I can discover when the sync changes, essentially. And I only can count up to 3 because sometimes, for some reason, this is not always true. So you get like 0, 1, 2, 3, 0, 1, 2, 3, and so on. But sometimes you get like 0, 1, 0, 1. And that also threw me off. So I wasted some time handling that stuff. But yeah, just count to 3 and then stop counting, basically. Solved my issue. And then what I do is that I check if horizontal sync and vertical sync are high, and also the clamp, then I'm basically in the active area. And yeah, I haven't really figured out what clamp does, but I believe it's sort of a overscan thing. Like maybe it's cropping a little bit. I still haven't really figured it out. The problem is that the Glasgow that I'm using, the RevB, actually it's a generic problem. The FIFO interface is not really that fast. It's quite fast, but not super fast because of high-speed USB and so on. So I'm able to get a throughput of like 40-ish, 40 megabyte per second. But the problem is that we need to have zero, like the FIFO buffers are quite small. So we want to be able to send a burst data of with quite high bandwidth. So this stuff runs at 50 megahertz, and the FIFO interface runs at 48 megahertz. So the good thing is that we should be limited to like every 3/4 of that time. Because of the whole sync signals, we don't need to send those back to the host computer. So sending pixel data is fine, but sending all of the data is not really fine because the bandwidth is limited. So I haven't really done a complete dump of this inside of Glasgow. I did, however, do that with the Salai logic, but that is like a completely different data format, and I didn't really spend time to write this code twice. So anyway, this works. So what this does is essentially, when the sync signals are high, I feed the FIFO with RG and B values. And then if one of the sync signals are low, I also check that the sync signals or the vsync changed. So essentially what this means is when a frame begins or ends, I guess, I will send one synchronization packet, basically. So the interesting thing is that we only need 7 bits per byte because of the we only have 7 bits, so I can use 1 extra bit for extra stuff in band. So it's kind of ugly, but it works. So that's it. That's basically it. So the cool thing is with Glasgow that this is basically all of the hardware logic I need for this. And then the Glasgow Python application framework gives me the FIFOs and USB connectivity and all of that stuff for free. So it's really cool. This is just some glue logic. So my FFmpeg. So what I'm doing is I'm running my applet, dumping it to stdout. Then I have this little C program that will look for this synchronization byte, which has a special bit set, and then synchronize the output to a fixed frame buffer size. Because sometimes, for some reason, the number of clock cycles with the active pixels varies. It's not constant. So that was also kind of a headache. Because usually, like with HDMI, for example, you sort of, once you get a stream of pixels, you sort of, yeah, it sort of follows the rules. But here, I don't know. Sometimes it just sends a little bit fewer or more pixels. So anyway, yeah, so I got that working. Then I also have the audio, which is sort of a PCM thing. So let me show the datasheet. I think I had that somewhere. I think we looked at that on the previous stream. So let's see here if there's audio interface. Right. Maybe I wrote it down here, the name of the chip. Yeah, there we go. So on the Nintendo 64, there is a DAC for audio, and it works like this. You have serial data coming in. So you have these are the samples, and then you have a clock, and then you have a left-right clock, which yeah, is active when the left or right channel is active. So it's very similar to I2S or so on, but the difference is how the data is aligned. So in this case, it looks like this. That this is actually not really true, because I spent some time in the logic analyzer looking at these waveforms, and it doesn't really match the datasheet. Surprise. Or at least I'm reading it wrong. I don't know. But anyway, you're getting like an extra data thing after the transition. So at least this part is correct, that you get a right aligned data packet. So the least significant bit is aligned to just before the LR clock goes low, and then you have 16 bits left of that. So yeah, I wrote some logic to handle this, to packetize that into samples, and then yeah, I had some issues with the synchronization. So when I started writing this code, I was using the raw pads, so not having them registered, and that was a big mistake, because then it turned out that I got a lot of sort of what do you call it, glitches where the phase seemed to change a little bit. So the data got mumbled up quite a lot. So it was basically sounding like pink noise or something. So anyway, using the flip-flop chain solved that issue. And this is a very basic implementation of deserializing the data. So I'm converting it to 16 bits, to a 16-bit register. And then because I was debugging, I was wondering if I had like a FIFO issue where I was filling up the FIFO to the computer or not. So I added a sigma delta DAC as well. So one of the FPGA pins I can just connect straight to a speaker. And that was quite fun, because that also sounded like crap when I had issues. But once I figured it out, it worked. And I was able to listen to raw Nintendo 64 audio. So I'm gonna do something fun now. I want to play the audio. So I'm just gonna prepare a command line. So I spent quite a lot of time trying to mix both audio and video. That was not fun. I had a lot of, I guess, Linux issues, because consuming two named pipes at the same time was problematic. So let's see here if I can figure this one out. think this might work. So I'm just gonna mute so your ears don't explode in case it sounds horrible. So just give me a second. All right, I'm gonna enable the audio. So there you have it. There is some live audio directly from the device. So yeah, it works. But yeah, so I spent some time trying to combine both audio and video. That was not easy. I'm probably just doing something wrong, but streaming out to... So I was able to get the Glasgow part done so that I'm able to write audio and video. Oh, thanks, man. So yeah, so I was able to dump both audio and video to binary files in real time. And then when I tried to use named pipes with the MK50, I was able to consume those named pipes using, cat and pipe it to dev null or something. But once I started using FFmpeg with the multiple inputs, I got issues. It seems that FFmpeg is consuming the data in, I don't know, in a weird way. So I wasn't able to get that to work. But I was able to dump the both streams to binary files and then consume them afterwards and combine them and mix them. That actually worked. So yeah, that was fun. So yeah, so the last 2 days or so, I was trying to finalize this stuff, and I kind of give up right now because what I have now is sort of good enough, and I want to continue doing something else. So that brings me to what I'm doing right now. So what am I doing now? I'm currently connecting. So let's rewind a little bit. A few days ago, or like last week, I made this really quick breakout board for the N64 cart. So because previously we were designing a full cart PCB with a ESP5 FPGA and a lot of stuff, and I kind of got bored of KiCading. I just felt like I'm not gonna be able to finish this and do something with it. So I will do that later. But in order to sort of get the flow going, I made this breakout board really quickly. So what it does is it just connects the cart up to the connector. Yeah. And so yesterday I received the boards. So that was super fast. JLC PCB, 2 layers, 1.2 millimeters. So I didn't order it with a V-score or whatever you call it when these are, in a 45-degree angle here. So I just used a Dremel to go over this edge, and that actually worked quite well. So I've now connected this board together with the FPGA that I was designing previously. Will you be selling this? Maybe. Who knows? It's a hobby project, and I don't want to promise anything, so to say. And I want to keep it as a sort of developer-friendly thing. It won't be a competitor to like Evercard or whatever it's called. It will not be something like that. So my goal is to learn how stuff works. And yeah, if anyone wants to build one of their own, yeah, you're totally free to do that, of course. And everything will be open source, all the code and PCB layout and schematic and so on. So yeah, but I just, the whole, yeah, we'll see. It's a hobby project, and yeah, we'll see how far I get. Maybe I will give up after a while and get bored. Maybe not. We'll see. Cool. Yeah, I mean, let me know. Yeah, follow me on Twitter and send a DM if you want to have a board and so on. But yeah, that is in the future. We will we'll get there when we get there. So right now, what I have is this board physically, and I have connected all of these, or not all of them, but all the important pins to the other FPGA that I have. So this is the connector of the other FPGA. So let's see here. So this is a board I made a while ago. And I just put this wide ass connector and thought, yeah, why not? Connect lots of IOs can be good to have someday. And yeah, today is that day. So I'm actually using all of these pins. Let's see here. Yeah, so basically all of this area here. But when I designed this board, I wasn't really that good at electronics, so I didn't understand the value of ground. So there is actually not a single ground pin here. So I have some ground here and I have some ground here. But yeah, hopefully it will work. We'll see. All right. So this board, it has an ECP5 FPGA with 45K LUTs, and it has SD-RAM, 32 megabytes, I think, and some other stuff. So this stuff we will probably not use. It's a FT601 or FT600, I don't remember, but it's a USB 3 FIFO interconnect so that you can send data back and forth to the FPGA using USB 3 in really high speed. So I think I get like 200 megabytes per second, which is really nice to have, but we will probably not use that today. Then here's some power stuff, and some LEDs and PMODs. So I guess now I'll start with the explaining the LiteX bringup. So yeah, so in order to create, so there are many ways to do useful things with FPGAs, but if you want to combine a CPU, an SD-RAM controller, and UART controller, and LED controller, and it quickly becomes complicated and complex and large. So there is fortunately a project called LiteX that does this for you. So let's just do a really quick overview. So yeah, it's this one, LiteX, and I think there's a ton of modules that you can use and plug in. So what it does is it's an ecosystem and sock builder that lets you combine different types of FPGA projects. You can basically just put them together, add some glue, press build, and now you have a working FPGA project. So I did that just now, like 1 hour ago. So let's have a look at that. So let's, I don't need that. So what I did here is I just created a directory for the ECP card 64. So maybe I should show that as well. 1 second. So this is where the cart stuff will live. So right now there's a work in progress KiCad project, and it's really not done. And right now I'm adding the LiteX stuff. So the entry point is the target. So in order to define what a project should do, like what it should contain and how it should be set up, you can create a target like so. So here I reused quite a lot from the Radeon ULX 3S board because it's kind of similar. It has an ECP5 and an SDRAM and a bunch of stuff, and then I just ripped out what I didn't use. So you sort of set up the stuff that you want to include. So here's some glue to just get the clocks going. So you can request the clock domains and instantiate some PLLs if you need that. You can actually sort of survive without any of this, just to get something up and running. Then you have this base sock class, which essentially extends the sock core, which does tons of stuff for you automatically. So what it does by default is that it gives you a CPU and some a BIOS that is built from C code, and it compiles that for that tool for that architecture, and then it includes that ROM in your bitstream, and then it includes all of your peripherals that you want. And in this case, we don't have a lot of stuff. We have some LEDs, and we have the SDRAM, and yeah, this is the place where you sort of add your custom endpoints, or whatever you want to call it, your custom hardware logic, and then you can expose that through the CSR and memory mapped addresses. Yeah, and then here in the end we just have some glue to some boilerplate for the argument, but that's about it. It's not a lot more. So we're reusing a bunch of stuff that's already sort of done for us. And then we have a platform. A platform defines the physical hardware. So stuff like pin mapping and individual like configuration, memory sizes, and so on if you want. So in this case, I've reused an old project where I used the same board. So we have our clock, we have our LEDs, we have some serial UART outputs, and then the SDRAM 5600, and then the N64 card. So here I defined the wide connector, like each of the pins here are mapped to a FPGA. Oh yeah, good evening. So each pin here is mapped to a physical pin, and in order to make sense out of the pinout configuration here, I can actually refer to a connector like this. So I call the wide connector a W. So just do W colon and then the index. And I made sure to map these indexes so that we have so it matches the numbering. So when I did the breakout board here, these numbers actually match the code. So that makes my life quite easy. So this wasn't a nightmare to write, because if you have to write like F3 and so on here, it's really easy to get lost. So I think this is actually a really nice way to do the pinout stuff. All right. So now we have a LiteX project, and yeah, because I'm lazy, I just did a one-liner here, hard-coded or almost hard-coded, for how to load the bitstream onto the FPGA. So that's what this does here. So the way you build this is that you run Python. In my case, I created a Python project with a setup.py and so on, because that makes my life quite much easier, because I'm able to do stuff like this. I can import stuff, and I could also do it relatively like so. Maybe that's nicer to do actually. Personally, I think Python and include paths and so on can be quite annoying, but by doing a proper setup.py and so on, it gets much easier. And if you do this, you can install it like so: pip install --user -e dot. What this does is it will install this package as an editable package, so it will just create symlinks to this path, and then --user will ensure that you don't get any weird global issues, because that can also be kind of annoying. So yeah, for me this works. That's just how I do it. That means that we can. Oh, sorry, maybe you can't read. Let's do like this. Yeah, here we go. Right. So in order to build the bitstream and also the BIOS, you can do like this. You point your module to your target, because here we have our main function, and --build will ask LiteX to build. So it will blast out a lot of log here. Let's look at the beginning, because that's actually kind of interesting. Here we go. So this is the beginning of the stdout output when building. Maybe it's stdr, I don't know. Anyway, it's the output when building, and it will tell you a bunch of stuff about the project, where stuff is and so on. So here it tells us the addresses of various things, like the ROM and SRAM, and it tells us that there is a UART and there's a timer, and the main RAM is located here, and it's this big, and so on. So this output is really useful. Yeah. So here's the complete, what's it called, memory map, and it will exist in header files and so on as well. So yeah. And then it builds the BIOS. I don't know how big the BIOS is, but it seems to have grown quite a bit in the last few years, I guess. Last time I did LiteX stuff was perhaps over a year ago. But yeah, it's time to dig into it again. Yeah, and then it builds the bitstream using the default CPU, which in my case is a RISC-V VIX RISC-V. And here we see that we don't have a amazing timing, but it passes timing, 58 megahertz. We run it at 50. So that, I don't know, might be problematic, because I'm thinking we might want to run the SDRAM at least at 100 megahertz. So there's actually a way to do 1 to 2 rate. So by asking the SDRAM generator to sort of run at the a factor of 1 to 2, the RAM should run twice as fast, which is nice. So anyway, after you have built it, you want to load it. What load means is that it will execute the bitstream flashing, basically, or not flashing, but programming. So currently I have it hooked up with a JTAG adapter, so it's just doing JTAG. So there you go. In this window, I have a serial console, so just a FTDI adapter connected to the board. And here you can see it actually boots. So let's just look at this and go through what it means. So when you see this, that means that, yep, it actually worked, but we haven't really done anything yet. So here it prints a bit of information about the configuration. And some of these values can be dynamic, or semi-dynamic. So it's kind of interesting to see when it boots. So in this case, I've configured it to have 16 megabytes, and actually, I'm not fully sure if this RAM that I have is 16 megabytes or not. It might even be 32 megabytes. Not quite sure. So I was looking at this just before I started the stream. So it does a quick speed test for 2 megabytes, and yeah. Right, I see. The bottom of the screen gets cut off, but yeah, there's not much interesting stuff going on there. So the BIOS comes with a bunch of features. I haven't enabled the Spy Flash. There is Spy Flash on the board, but I thought for bringup, I probably don't need that. So the BIOS allows us to do a bunch of stuff. We can, read memory and calculate CRC. That is really useful when you're sort of bringing up storage and so on. So it's really nice to have that. So what it does is it just calculates CRC over a memory area. So you can test stuff like memory accesses and test your peripheral. Serial boot allows you to write over serial port a program that is then executed. So essentially, like you would expect from a bootloader, it lets you boot something else. And there are many ways to do this. But the simplest solution is to use a UART. But there is also you can have a USB peripheral where you get what's it called again? An ACM port. So you get a virtual UART, and over that you can also load your application to boot, and you can have Ethernet, and there's a bunch of stuff. It's really cool. And then here's some memory stuff. So I actually haven't really tried these new features. New to me. I guess they are probably over a year old by now. But yeah, I want to do a memory test. I will need some address. So I guess we should go from here. And then we want to have, let's see here, we can do 16 megabytes. So let's see if that works. That seems to have worked. That's cool. So I have no idea how memtest works. Because something that might be a bug is that you have too much memory allocated so that it wraps. So if you start writing over the whole memory area, and then immediately after read it. But yeah, here it does actually write first and then read, like in a completely synchronous way. So that's good. So this sort of, if the pattern it writes and reads is sort of interesting and unique, I think we can trust this. So that's cool. That means that we have actually 16 megabytes of memory that works. But I honestly think that I have 32 megabytes because I was looking at the datasheet of this one. There we go. So it's 256 megabit. So I have actually a hard time reading these specifications, like 16 million times 16 watt. So yeah, anyway, the way I configured it was to use this geometry. We have two banks. There's a maybe there are more banks. I'm not sure, but we have two bank pins at least. Then we have the rows and columns. Yeah, going by the address, number of bits, and yeah, I guess that might be correct. So anyway, I want to change this to 32. Here we go. Yeah, so I need to build a bitstream again. Luckily, because of the open source tools, this is actually quite fast compared to the proprietary toolchain. So yeah, this should just be 1 minute or so. Should be quite quickly. So here we can actually look at the usage. Here we go. So yeah, we have a lot of space left, but this is actually the 45K variant of the FPGA, and I think I'm gonna go for the 12F or 25F, which is basically the same. So yeah, it would be nice to sort of keep this relatively low, but we don't have to optimize it yet. So yeah, we're at 5,500 and we have like, I don't know, 25. So it's still a lot of room. Yeah, and there it's done again. Let's see here. Yeah, this one is the interesting one, I guess, because it shows everything in a nice way. Yeah. So again, we are at 4.5K. So there's a lot of room. Yeah, and then we want to load this, so we just use the load again. And I think it always builds the BIOS because software is, yeah, I guess it's safer that way. And it loads. Yeah, here we go. Right, so now we could actually run this again, the mem test, just to test that we still have 16 megabytes, and then that seems to be the case, yeah. And now I want to do 32 megabytes, see if that works. So, no, it does not. Okay, so now the question is, why doesn't this work? So what happens now is that it stalls for some reason. Actually, this looks kind of funky. So I guess there is something in the configuration that limits it to 16 megabytes. And it could be so simple that I just don't really understand how to set this geometry up. And honestly, maybe the banks should be 4, because there are 2 bank bits. So you have 0, 1, 2, 3. Yeah, maybe that's it. The banks should probably be 4. So yeah, let's build another one and see if that helps. Because if you look at the pinout and datasheet, you see that there are 2 bank select pins. So that gives us up to 4 different values. And yeah, we have 13 address bits and 16 data bits. Yep, almost done, I guess. Just give it a few minutes, or 1 minute. Yeah, so once this is done, we should be able to start working on the code, or at least start thinking about it. So let's just finish this bring up. I'm not really sure which approach I want to take, but I guess writing it fully in C, porting some C code will be fun. And then using the GPIO subsystem or GPIO module to expose the CIC pins. Okay, it's done here. So let's load it and see what happens. Yep. I don't know. I was kind of unmotivated the last 2 days. Didn't really get a good flow at all. But now I do. So that's why I'm doing this now. So yeah, let's test 32 megabytes. See what happens. Oh, it passed 16 megs. That's good. And it seems to work. Huh, cool. So now we have 32 megabytes of SDRAM. Perfect. All right, there was one extra thing I wanted to change. The SDRAM rate. I want to try that at twice the speed. So how do we change that? So the easiest way is to just change the default, I guess. I'm just gonna do that. But there's an argument to change it as well. But this is, I mean, this is the intended configuration that I want to use. So let's just change the default instead. That makes more sense to me. And this is also just a sort of early bring up board. So yeah, as you see here, I added the Kilsyth board and target. But the ECP card 64 will be like the actual final board, which will probably be very similar in terms of Gateware. Probably different pins and different package for the FPGA and so on, but otherwise, like architecture-wise and code-wise, it should be very, very similar. All right. So now it seems that we were not able to meet timing. So it's working harder. Okay. Again, 61 megahertz. That's perfect. Cool. So let's try it. This will be interesting. Okay, it's definitely faster. Definitely faster. Or am I just dreaming? So we got the write and read speed here. That is exactly the same as before. Kind of weird. Maybe it's the CPU that's simply slow. I don't know. Because the CPU is running at 50 megahertz and in the bus with the 16 bits. So I mean, theoretically, it should get like 32 bits per CPU clock cycle. So theoretically, we should get 50 megahertz times 4 bits per clock cycle, which is 190 megabytes. But that's I don't know. Yeah, I guess we're losing a lot of performance because of how the CPU works. Maybe it's a 4-stage pipeline or something. I don't know. Or maybe 8 or 16. Okay, 16. Now the values seem to match up slightly at least. So, and also it could be the code that does something stupid, I don't know. Like the actual memory read and write maybe takes up multiple instructions or something. I don't know. In any case, the memory controller should at least be running fast. So I guess later on we should add some gateware that gets exclusive access to the SD RAM and can then perform read and writes in a sort of controlled way. All right. So let's continue. Where do we want to go now? So I guess I can start looking at the CIC stuff. So up until now, I haven't really had to connect the FPGA to the N64, but I have it here besides me, so I'm able to connect it if I want to. So I guess what we can do is to look at a different project that does this already. So we have a bunch of approaches that we can do. One is to look at the Ultra CIC 3, which is a CIC implementation for an AVR, but it's written in assembly, and I really don't speak AVR, and the code is like 1,000 lines. So I'm not gonna do that. Instead, there is this project, Karte, and let's see here. So this is another open source FPGA-based flashcard for the N64, and we looked at this on a previous stream and actually used the PCB layout as a template, and it fits very well. So this is actually a very early revision, I think, because the one that I used had nice corners, as you can see here. These ones here, and those were, yeah, it fits really well. So I really can't complain about that. That works perfectly. And it also sits snugly in the cart holder. So anyway, this project it has a similar architecture, I think. It's actually using SRAM, a big SRAM. I think. All right, it's quite a different architecture. It has a lot of QSPI flash, and then it has SRAM. Right. But anyway, there is Gateware for this, and there's also a soft CPU. So inside of the FPGA, there is a soft CPU that emulates the CIC chip. And I was thinking of, yeah, let's start with that, because the boot process of the N64 was actually a really good explanation about that here. And there was some talk about this this morning as well in the Discord. So yeah, here is the boot process. I really don't understand this on a deep level. I have just barely scratched the surface, but it's I think I understand the concept at least. So yeah, I actually don't know what IPL stands for, but it's yeah, this seems to be the boot process at least. So yeah, the PIF is the let's see here. Let me just so yeah, here. So the PIF is the peripheral interface chip that handles both IPL. Ah, cool. Ah, yeah, that sounds reasonable for sure. So the funny thing about the PIF is it does multiple things. It's both peripheral interface for the controllers, but also handles security. So this one is the chip that contains the bootloader ROM, but also communicates with the CIC chip on the cartridge. And there's actually an open source FPGA implementation replacement of this chip that doesn't do CIC, so that you're able to boot your Nintendo 64 without having to bypass the CIC or emulate the CIC chip on the cartridge, which is kind of cool. Initial program load. Okay, cool. Yeah. All right, it says here. I'm blind. So yeah, that's really cool. So if we go back here to the process, so it boots from the ROM, sets up some stuff, and then it copies the second stage bootloader from ROM into memory instruction. So ASP stands for the signal processor, I think. Um, inside of the reality coprocessor, we have the signal processor and display processor. And this is like the second big chip. So the CPU is separate, and then the CPU is connected to this one, which is in turn connected to the RAM. So in order to access the RAM, the CPU has to go through the reality coprocessor, which is kind of interesting architecture, but yeah, that's how it works. So anyway, eventually we get this IPL2, which in turn starts talking to the CIC chip. So I guess once I start probing the signals, I will see stuff from this part and onwards, from the cartridge point of view. Yeah. So this stuff, this will generate a ROM access. So if we go to, where was it again? Here. So it's kind of interesting. Like if we look at the signals from the cartridge, like what is actually the absolutely first thing that happens? I honestly don't know. We'll have to go through that. There was some talk about this parameter here. The first word read is the cart header, which sets the bus speed for subsequent cart access. And that could actually be, because I have this super jank setup with the flying wires all over the place. It might actually be a good idea to use this slower timing configuration so that signal integrity won't be a big issue. It might still be an issue, who knows? But I think it should be fine. But yeah, who knows? So anyway, yeah. So I think we can. There's like so much I need to do. So I'm not really sure what to do first. But now we have the LiteX stuff running. So we have a CPU running. We have RISC-V. And I'm also thinking about like what is the best approach to sort of write the code that I need. Probably I should write like a separate application that is loaded, but I could also just hard code stuff into the BIOS. I could be super lazy. But I think I should look at the FPGA implementation of this project, the Butzelkarte, because it shows me stuff about the bus. Like maybe there are some signals that I need to pull high or low. I think there's an interrupt pin that it should have the correct. I think it should be high, and stuff like that. So I guess we can look at that. So let me just prepare. Let's see here. So we can put that over here. Yeah, so this is the Butzelkarte entry point. top module, I think, and it's written in VHDL. And I've written one line of VHDL in my life, but I think we should be able to read it anyway. I hope so, at least. So actually, this is the top module. So let's just have a look at the top module. So I guess all of these are the N64 prefix signals are the ones connected to the cartridge. So yeah, that makes sense. Yep. So the way I did this was to expose them in this way. So we have an N64 card, and we could actually call this N64, makes the names shorter. And we could actually just double check so they match. Here they call it ADIO, which I don't know. I can call it that way too, I guess. Why not? This one I'm not really sure what it does. EPS dot. I guess it's this one. Right. So yeah, I think I have all of the signals here because this is so again from my hacky setup. Hello, Dragonmux. Yeah, so here's the PCB, and I to make my life easier, I created a connector here in the schematic which matches the board that I'm using. So these are the signals that I have connected with cables. So going back, I guess here, yeah. So all of these signals are actually connected. Hey, Sten. All right. Yeah. So all of this stuff is connected, and right now I'm trying to figure out. So there's a VHDL implementation of a flashcard that I'm trying to. Oh, thanks for the raid. Awesome. Yeah, I mean it's kind of late, but I have vacation, so it's fine. I'll keep going for a while. Not sure how long though. Yeah. So anyway, I will try to make sense of this VHDL code and see what I need to sort of get to an early boot stage and see how to interact with the N64. So yeah, this will be kind of exploratory, but there is this reference that I can look at, so that's cool. So just to give people who just joined a really quick overview. So I'm currently working on a flash cartridge for the Nintendo 64, and in order to prototype quickly, I made this super simple cartridge breakout board. And right now I am using a different FPGA project that I did 2018. Holy crap, that's a long time ago. Time flies. Where I had this wide connector. So I thought this could be nice to use someday. And yeah, today I connected it. So yeah, I'm gonna use this as a sort of dev kit to bring up my project before it exists. So I just spent some time explaining how the LiteX project works. So let me show it quickly here. So I set up a LiteX target and platform for the board. So yeah, it defines SD-RAM, some clocks, and yeah, stuff that you need to sort of bring up a LiteX project. And yeah, oh, Icebreaker Bitsy streams were in 2018, and only yesterday I have put them finally in stock on store. So tell me about old projects. Congratulations on actually finishing it. That must be a great feeling, I'm sure. iStudio. Yeah, I've never tried it actually. Should give it a shot, I guess. Yeah, yeah, the reason why I started streaming is because I've got the LiteX project up and running, and I have the BIOS running here on the hardware, and we have the memory test here. It runs, it works perfect, and I'm just so happy about LiteX. You just configure it and it works. It's amazing. So the idea is to use this as sort of a framework for yeah, for the project, and reuse the SDRAM controller for loading flash cartridges and programs and so on. But yeah, so the security of the N64 is kind of interesting. It's about the CIC chip, which does some magic. Creates I honestly don't really know how it works. But the gist is basically that the N64 sends a signal, communicates with this chip, and expects a certain value in return. And based on that, the boot process continues or halts, or it doesn't really halt, but it runs at 1 hertz instead of megahertz. And I think it stalls. But anyway, yeah, that's about it. So I thought, as a first step, I could try to port some code so that I can emulate the CIC chip, because that code exists. So again, I was just showing this a few minutes ago. Okay, I'm lost in my. Here we go. So there are a few variants. The Ultra CIC3 is a firmware for an AVR. And I don't speak AVR assembly, so, and this is like 1,000 lines of assembly. But there is this other open source flashcard, the Brutzelkarte, that is actually implementing this with the C code and the soft CPU. But I haven't looked at it in detail, but from what it seems, it should work. You don't want to be able to talk AVR assembler. Yeah, it's an interesting name. I don't see any smoke yet though. We'll see. Hopefully, hopefully there won't be any smoke. So anyway, I was thinking of because this project has been sort of confirmed to work, at least for running homebrew. So that is my goal as well. So that's perfect. So I was thinking of just porting that code and using a RISC-V CPU. I don't know which one. Maybe something small like the serve, perhaps, because it's kind of funny. But maybe it's too slow. No, I don't know. I think the data rate is like 1 megahertz or something. Anyway, we have the VIX RISC-V for now, which should be fast enough, I think. Yeah. And so I'm not really sure what my next step should be. Like, how should I start looking at the porting firmware, or start setting up the bus so the N64 can actually enter the whole booting stage? N64 is just a memory bandwidth from my SK. Oh, okay, I get it. The architecture is really interesting. I think there was some good overview somewhere. Was it here? There is a bunch of information, and I still am struggling to sort of find my way around stuff. You end up with like so many bookmarks and information overload. But the N64 Brew wiki is really, really good. This is like a very active wiki where people are updating and improving the articles every day. That's cool. Oh, I see. Interesting. All right. Yeah. So I guess a good approach would be to look at this VHDL code and try to understand which signals we need to sort of pull high and low just to sort of allow the boot to start. So yeah, here we have those signals. So this is the top module, and it just instantiates this and sets up a clock. So not much interesting stuff going on here, I guess. So let's jump into the implementation. So I guess this is the flash. It's RAM, I think. And then some EEPROM. I guess this one is interesting. Yeah, that's this file. So yeah, here we have the bus address or the bus IOs defined. Yeah, let's keep that in mind. Some SRAM. Yeah, okay, and here we have the CIC stuff. So that's interesting as well. Wow, that's a lot of UART. Maybe it's printing debug information about everything. That's probably why it needs all of the signals. A bunch of stuff. All right, yeah. So if I remember correctly, this cartridge also allows the UART to be accessible from the N64 bus. So that's probably why there is a bunch of glue code around that. Mm. Okay, it's instantiating some stuff here. There's so much just connecting stuff together here. Wow. Quite a lot of boilerplate code. Okay, here it gets interesting though. So the cold reset seems to be an input. That's interesting information, I guess. So I suppose that is yeah, sampled from the N64 side. So do we do anything with that? Okay, it gets inverted and stored into the N64 reset register. So I guess that is sort of a master reset thing, like a global reset, I suppose. Yeah, okay, so I guess it goes high when it boots or something. Ah, anyway, that's interesting to know. Yeah, my brain, when I see VHDL, I always get confused. Like the direction of this arrow is like, I guess I can look up how this works, but I suppose this is just connecting those together. Um, Okay, and here's some initial state. So this is actually, I guess, the most interesting thing for me to know. Like, what are the initial output states that I need to handle? So the NMI should be 0, which is interesting. I thought it was an interrupt that was inverted, because that's usually the case. So I guess the interrupt is being raised when it goes high. And then here we have the initial sampling for the address low and high, and then the read and write. Yeah, okay, so that's actually not that interesting. Okay, so now it's time to write some Gateware, I think. So going back to our project here. Yeah, now I'm actually not super good at writing this from scratch, but we need to. So this is Migen and not N-Migen. I'm a little bit rusty on that right now, but let's do like this. Something like this. Then we also need to sort of implement this. Yeah. This will be sort of exploratory. I will probably make some weird mistakes. Yeah, so we need some name. What should we call it? I hate naming things. Let's just call it cart. And then we need a way to import it. So something like this, perhaps. Yeah, now I need to remember that this is in Migen. So I think I should just look at some hopefully simple code and copy that. So let's just take the lead chaser and copy that. So N64 cart. Then we can just make something simple. We don't need this. So again, don't look at this as sort of a tutorial, because I honestly don't really know what I'm doing. But it's yeah, I'm exploring, hopefully doing something right. So we don't really need. So what do we want to do? We want to control the N64 cartridge I/O pins. So let's yeah, do we want any CSRs already now? I am not really sure. Let's not do that. Or yeah, I guess we can just keep some placeholder. So what I want to do now is to sort of replicate the initial state of the I/O pins. So the way I defined the IO, the IOs, is that I have this N64 group. I'm not really sure what the word is for this, but it's a group of signals, subsignals. So I need to request these somehow. It's been a while, and I am really rusty. Because this is in Migen. So the way the LEDs work is that, let's see here, going back to the target. Yeah. You can do this platform.request, just like we did here with the SDRAM, which has a group of signals and so on. So I guess we can look at that implementation to, yeah, kind of understand how to access the group signals. But I think you can probably just do pads dot and then the name of the subsignal. So pads dot CIC DIO, for example. So just taking this one, for example. All right, that was a bad example. Let's go into here. So on this screen, I have the LiteX code as well. Yeah, so yeah, I see. Yeah, that seems to be the case. So you just do ads dot the name and then dot whatever. I think so, at least. Anyway, let's see what happens. So one sort of negative thing with the LiteX is that it's building a lot of stuff. So when we sort of want to iterate on something smaller, it takes a little bit longer time because it takes like a full minute to build, including the CPU. But it's, I guess that's the price you have to pay. I mean, what we could do is to sort of break out the, yeah, the CIC part. But I mean, I'm gonna use the CPU, so yeah, that doesn't make any sense. So, I guess let's just start coding. So I was thinking actually if the CIC pins should be separated because I think I want to expose them as GPIOs for the CPU. I'm thinking I should actually do that. So now it's going to be a little bit of copy paste code, but yeah, bear with me. So let's jump to the Radiona, not that one, but this one. So this is the platform definition of the ULXS3S, ULX3S. And here we have a bunch of GPIOs defined like this. And if I'm not mistaken, these are then exposed as GPIOs. Maybe automatically, I'm not sure. But we could do like this, which is cool. So I guess we can start doing that. So instead of having a full like N64 group with all of the signals, we can split them up. Let's call this N64 CIC. Let me just check if we need any more pins. I think this one you might need as well. The S-dot. I think it was that one at least. Yeah, that's details. We can always look at that later. But the point is to sort of group that stuff away. So I've actually never used the GPIO stuff in LiteX, but I suppose okay, you can have an in-out as well. That's really cool. So just like a regular GPIO, you can probably configure it through CSRs. Right. Oh, and you even have the IRQs. That's cool. Okay, so now we have split out those signals. That's cool. We can group this so it's a little bit nicer. So I'm not really sure what CR is. let's try to understand what that means. All right, it was the cold reset. I think I can actually rename that to something more useful. Cold reset. All right. Okay. Yeah, and that definitely makes sense to have in this in the N64 cart, so to say. Yeah, let's just call it N64. So yeah, just to give a recap of these signals, here is the address and data I/O pins, and we have the cold reset. Maybe this one should be in the top. These two signals define how, if it's the high or low part of the address that is being sent. So this is a capture of the bus during an access. So yeah, this is what happens. All right, let's go here. Yeah. So we have, and the read and write are self-explanatory, I guess. I'm not 100% sure exactly when I should sample it and so on, but we'll figure that out later. And here we have the serial in, I think. Let's see here. Was it here? Yeah. Right. So yeah, I based it off these names. So 1.6 megahertz. I think this clock is what drives the CIC communication. But there's also the CICD clock, so I don't know. Maybe it's a separate clock, 3.14. We'll see. Anyway, here we have the pins. So in order to expose them as GPIOs, we need to do this stuff. So I think you need to do one GPIO per pad. No, you can actually do multiple pads. Okay, that's cool. So, okay, what we're gonna do now is we're gonna make one GPIO group or endpoint for the whole CIC chip. I'm not sure it makes sense to keep the clock there because you won't be able to do anything useful with that with the CPU, I guess. But yeah, let's start there. So anyway, there we have the card stuff, which we will add soon. Right, we need to import some module. Let's see here. There we go. So yeah, again, LiteX comes with a bunch of cores, which is super useful. You just plug and play, off you go. And honestly, I'm gonna keep these at, or use these at in outs, I guess. Doesn't it work? There we go. So we're gonna use in outs so that we're able to change the N64 CIC GPIO on demand. Because I think, yeah, the DIO sounds like it's in both directions. So yeah, that's cool. So now we have that. We should write some code for the N64 card stuff. So going back to this, so now we understand a little bit more how LiteX works and how Migen works, because yeah, it was a while ago. Need some recap, but essentially we can access all of these signals just using the pads, period, and then the name. So that's really useful. So I'm just gonna put a copy here for reference. There we go. And then let's just clean up a little bit. So, all right, it's a different style. Okay, I guess we can. Let's just do like this. Right, I have them here. Need to cheat. I've forgotten so much in Migen. I need to keep this here for reference. All right. When you have input outputs in Migen, you have. I know how it works, but in Migen, I forgot. So I need to look that up. All right. Yeah, so I need to do this stuff. The TS triple thing. So I think when I do the pad request, I get the raw pad, but I still need to do the TS triple stuff myself. Okay, I guess that's just on boilerplate we need to do. Because like, right, because in Migen I'm able to specify the pin type if it's an input or output. I'm not sure if you can do that here. Anyway, I'm just gonna do the TS triple stuff. All right, I'm gonna need the multi-rig, I think. Yeah, because again, if I don't misremember, this is the same thing as the what's it called again? The FF synchronizer in Migen. So it takes the external signal from the outer scary world and synchronizes it with the or a clock, which in our case will be the 50 megahertz system clock. Yeah. Okay. So I guess we can do something like. Actually, there are not that many. Or actually, there are. So this is actually for all of these pins. So let's write some nice Python code. Yeah, for I in range 16. So now we're creating this TS triple thing for all of the IO pins. So I'm just trying to figure out what a sane way is to sort of do this. Yeah, so we want an output enable signal, but do we want to change that? I don't know. I mean, I guess we can actually have something like this. Yeah, so we have one signal that controls the output enable of all of the I/O pins. That makes sense, I think. And then the output, um, I guess we can have a signal for that. That makes life easier. Something like this. No, not like that. Yep. So now we have a signal that's 16 bits wide, and we can connect that with comb logic, like so. I think that makes sense, right? So outside of this stuff, we can set the output enable 1 or 0, and then the full AD out. Yeah, I think that's interesting. Then we can also do AD in and do the same thing but inverted. So just like that. I think this actually makes sense. So now we have wrapped all of the address bus as an input and output. Yeah. And the initial state will be that output enable will be 0. So it will be an input, which is perfect. And yeah, that's cool. And then these are all inputs, and I think we should use the multi-reg stuff for that. So, because again, this takes an external signal, and I think at least. What does wrap do? All right. Okay. This took me a bit of brain power to parse, but yeah. So this is the actual implementation. Okay. So it creates a register for each N, and then it forwards the signal. Yeah. That makes sense. So just to explain this again, it takes the input from the outer world, the pad, and it passes that to a chain of flip-flops. And those flip-flops are clocked at the system clock, or with the system clock. So, yep. Cool. And so we want to use this multi-reg stuff for all of the inputs. And actually, all of these are inputs. Also the cold reset. So, I guess we should just create signals for that. So, that is a bad name. Read. Let's do like this prefix. Something like that, I think. Yeah, I think this makes sense. So now we have stable signals that we can trust. That's good. So now we can sort of look at the initial state. Right, there was some interrupt pin. Did I mess that up? Probably. Yeah, there's supposed to be an interrupt pin as well. So where did that go? This one, the NMI. That is on pin number 4. Okay, so let's add that. Because that could actually be a big problem. That's the wrong project. Sorry. So NMI, that was on pin 4, right? Do we have anything else? I think that's it. Yeah, I just missed that one for some reason. Yeah, sorry. Okay, cool. Now we can go back here. And I can delete this because all right, we need the NMI, and that is actually an output. So I guess we can do like so, and then just do yeah. Now we have like a local. Everything is prefixed with N64, and we have local signals, and they are then connected to the real world, or the other way around. So I think that is a good starting point. So going back to the VHDL code, so they used the cold reset as sort of a reset, which makes sense. All right. Yeah, and that was connected to the N64 reset. Yeah, that makes sense. And the N64 reset in turn is used in a bunch of places, among others in this place, which resets the sort of. I don't really understand why they reset these, but I guess makes sense. Anyway, the NMI, that is the interesting thing, I guess. So I will set that to 0. I guess we can do something like yeah, this is how you do it in Migen. So on a cold reset, we set this one to 0. I forgot how you did multiple things in an if case. It's not that important. I think you just use a comma. Yeah, right. If, and then yeah. Yeah, okay, here's a good example. So you can actually do multiple things you just add a comma. So for each statement you want to execute in that if case, you just add, like here as well. Good to know. So yeah, in our case, we don't need to do that much. And 0 is also the initial state, so should be fine. Okay, so now we have an initial state. Perfect. But now, yeah, I don't know. It's getting a little bit late, but I still want to sort of do something. Trying to figure out what the good. I guess we can try to build it because I don't think this. I haven't tried to build it, and this will probably break. Yeah, it broke. What does this mean? Ah, right. Okay. I think I need to do the TS triple stuff outside for the CIC stuff. So that's interesting though. Okay, let's do like this. N64 CIC. Here we request those ads, and then we create a GPIO for each signal, or for each sub-signal, so to say. Yeah, and we had these ones. So as I said, cheat sheet. Let's keep them here. So I guess that's an input. I don't think we have either inputs or inouts. Yeah. Yeah. Let's just comment this out. So I think you can do this. This gets a bit redundant, I guess, but I guess we'll manage. Let's do this one. I'm still kind of curious about this pin. I don't really know what that does. Okay, there are two data pins. So it's 18 and 43. Let's go here, 18 and 43, this one. So it's this one and this one. Yeah, so these are the two. So it's the D clock and DIO. We have the SI clock. Yeah, pin 21. Yeah, this one I wonder what it is. Okay, here it says it's round. That's interesting. 21 is actually a stat. Oh yeah, I was blind. Sorry. Stat. Just. I don't know what that is. We have sdata. S.io. So just to match these with sort of my code, we have this one over here. Yeah, I'm just gonna move this over here. So SI clock, it's this one. CSE DIO should be this one. And we have the D clock, it's that one. And then the EPS that has to be this one. That's also an IO, so that's good to know. Input output. Okay. What is there? Yeah. So that means that we need to put this one in as an IO as well. So yeah, let's remove those, and then we need to create. This is a little bit annoying. So we need to do the T's triple stuff. I'm kind of curious. There has to be someone who's used those in out. No. So I'm interested in the output enable. Okay. I guess there's first for everything. We're gonna need a CSR. It just feels like someone must have done this before. So my question right now is, okay, there is a GPIO tri-state. Good. That is actually what I want to use, because I want to control the control the output enable with the register. So yeah, this is what I want to do. And you just, oh, that's perfect. Cool. That seems to be super easy to use. So instead of doing like this, we just do like this. And we do like so. Oh. And then we also need the SI, no, EPS dot. There we go. Then need to include this one. So just to recap what just happened, I found out that using the GPIO tri-state class handles the whole tri-state stuff for me, so that you get the register or a CSR to enable or disable the output, and then you have a both input and output GPIO. So that's perfect. So now we can build this and see if it builds. Wish you a great tinkering time. Bedtime for me. Catch you next time. Yeah, thanks. Thanks for stopping by. Oh no. Okay, so it seems that my fancy reference in the platform file didn't really work. So I've used this previously, but it might be an Migen feature. I don't know. I'm gonna have to cheat a little bit. Let's see if there are any connectors. Yeah, there are. So what I'm looking for now, or if anyone in chat knows, how to reference a connector from the IO definition. So what I'm trying to achieve is that I have this huge connector defined here with the pad names. And then here I have the signals with references to that connector, because these numbers make sense to me. That makes my life much, much easier. But I guess at this point I could theoretically replace, but that's a pain. So again, this is Migen, which I haven't been using in a while, so I don't really know how it works. And the whole connector. Okay, so here's the connector manager. So let's see if there's actually a colon here. So resolve identifiers. That sounds like exactly what I'm trying to do. So what's going on here? Let's read the error message properly. Key error W. It cannot find W in the list of identifiers. So I'm gonna print that one. Okay, it's empty. So the connector table is empty for some reason. Why? I have this. Oh, I think I know why. I should do like that. I forgot to add the array of connectors to the actual platform. So let's see if it works this time. It seems to do more. So that's cool. So I'm just scrolling up here a bit to see the beginning. Here we go. Right. So this is the contents of that, what I'm printing. And indeed, we have W, and the indexes here are actually correct. Cool. So that means that I can remove that print. Perfect. And now there's some place and route going on. And while that is running, we can actually look at the generated software. So in the include directory, I think, we get the CSR, which is generated. Everything here is generated, but it's generated based on our unique platform or target. So I guess what I want to look for is GPIO, but there's nothing. Okay, let's maybe I forgot to do something. I mean, I definitely forgot to do something. Question is just what? So I added submodules like so, but maybe I need to do something about the CSRs. So let's have a look at the Radiona example, or not example, but board targets. Yeah, GPIO. Yeah, it just adds it as a submodule. So am I missing something? Because the LEDs are added like this as well. They have some CSR as well, right? So let's just have a slow look at the various headers. Okay, so it should be in the CSR.h. Maybe it gets generated later. Oh, here we have the CSR for the LEDs. That's interesting. Oh, the names are okay. This is good to know. So the name of the GPIO CSR became the name of the submodule. So it's called N64 CSE declock. Oh, yeah, and here we have the output enabled, the tri-state ones. So I guess it's not a bad name. It's just a little bit long, but it explains exactly what it is. So I guess it's not that bad. Okay, so now we have GPIOs for this. Bring back to, I guess, targets. Yeah, so this becomes the actual name of the GPIO. Yeah, so the question is now, where do we go now? Should I... I'm not really sure. But yeah, it's getting late. It's almost 3 a.m. I think this has been an interesting bring up for sure. We now have the GPIOs configured for the CSE chip so that when we run a CSE software implementation, we can access those GPIOs just like it was an ordinary microcontroller, nothing strange, which is perfect. And then for the N64 bus, we wrote some boilerplate or whatever basic stuff that handles the inputs so that they are being registered, and the outputs so that we are able to access it in a sane way, which is good. So I guess the next step would be to integrate the CIC software. But yeah, that will be something for tomorrow. So I think I'm gonna end the stream now, and it's been it's been interesting. And it's been fun. So yeah, until next time. Yep, see you. Thanks for stopping by.